Okay? And then of course we get the same factor that we had before. Minus 1 by 12L. Same derivative thing. And this may be very intelligent to start. And declare this to be the answer. That would be wrong. Can somebody tell me why that's wrong?
Maybe there is a finite part factor.
Exactly. Exactly. Good. You see, let's look at what we want here is to keep track of, you see, this x variable, let's replace this by variable y. Then y is not integrated from 0 to infinity, but from a to infinity. So any dependence of the answer on a we have to keep track of carefully, because that's what we are after. Okay? So this thing is 0 to infinity of this minus integral 0 to a of y by l. Now when we are integrating up to a, which is finite numbers, this part is not. Okay? So that gives us a factor of minus a squared by l. This is now universal and truly independent. Okay? So the answer for this 0 point sign is what? It's minus 1 by 12. Now I'm dropping the L's. Everything is proportional to 1 by L. Okay, minus 1 by 12 plus a by 2 minus a squared. Okay? Now let's focus on the problem at hand. For each of the left movers and the right movers, we wanted n by 2. The 0 point energy has a by 2 in it. Okay? So the contribution to L0, so L0 0 point, is equal to minus 1 by 24. Same thing that we had before. Okay? L0 0 point is minus 1 by 24. But then we get plus a by 4 minus a squared. Now substituting the a is half, you get, substituting that a is half, we get a by 8 minus a by 16, so L 0 point is equal to minus 1 by 24 plus 1 by 16. Okay, this happens to be equal to 1 by 48. But that's not important. The really important thing is that there's an additional factor of 1 by 16 compared to what we had before. Okay? So what does this imply? This implies that, okay, so now what do you get from quantizing this twisted sector state? In this twisted sector business. What you get by quantizing this twisted sector is the Fock space of all no zeros, the Fock space of all oscillators with half integer pointed numbers. But we have to keep track of the 0 point condition. That's important for the physical state condition. Okay? Now, when we had this minus 1 by 24, the physical state condition was n squared alpha prime n squared by 4, okay, was equal to n minus 1. This was the usual. That minus 1 came from minus 21 by 24 for each of the 24 physical directions. So we continue to have this n minus 1, but then we have a plus 1 by 6. Is this clear? vacuum energy of the overfold twisted sector vacuum in the overfold conformity theory, the energy difference between that and the vacuum of the untwisted state is an L0 equals L0 bar equals 1 by 16.
So what are the oscillator conditions here?
That's the same thing. So, I mean, of course, you can work in any variables you'd like to. But if we normalize the correct factors 1 over square root n, where n is the frequency, you get the same thing. You get
So the frequency should be n plus r.
yes. So let's label the oscillators by their frequencies, which are allowed to be half integers. Okay. So for alpha n alpha minus m, if you want to use the same formula, just use the same thing with m times n times, where m is the frequency, it's the half of the oscillator. Okay? Of course, if you wanted it, you could work with oscillators normalized so that this is 1. But then it's the frequency that will enter the energy form. That's clear, right? It's it. The energy of a quantum of a harmonic oscillator is its frequency. That's all. Okay? With this convention though, you use all the same formulas that we used. First, the expansion of the x field will continue to be given by del x will be given by the same formulas we had before in terms of alpha m, except that the frequencies of the oscillators will be shifted to half amplitude. That is what we use then with this. Okay? Great. Now, why is this important? So this full overfold field theory, this full overfold conformal field theory, has two sectors, the untwisted sector and the twisted sector. And the twisted sector, we've seen that in the vacuum has an energy 1 by 16, 1 by 16 that's higher than the energy of the untwisted sector. Now what does that mean? In particular, you see, every state in the conformal field theory has a dual operator. In particular, the vacuum of the twisted sector has energy 1 by 16, 1 by 16 higher than the vacuum of the untwisted. Now, that translates into the statement that the dimension of the operator that is dual to the vacuum of the twisted sector under the state operator line is 1 by 16, 1 by 16. Now, working on actually what, this operator is a pain in the neck to deal with. This operator is called twist operator. It's the operator that actually, well, it does something, it doesn't matter. In the case of the circle compactification, we managed to find, you see, the definition of this operator is that that the insertion of the operator ensures that we're doing a path integral with field configurations that obey boundary conditions that such that x goes to minus x as you go around the operator. That's the definition of the operator. That's a sufficient definition. And it's the lowest energy thing you can do with that. Because then you could put that times other operators, times explicit insertions. Okay? And this is, when you think about the sufficient definition of the operator. This is the analogous statement of saying that the real definition of the operator in the winding sectors was that the x field winds as well. But for the winding sectors, we found a nice trick. That allowed us to write a very nice, simple formula for this operator. Nobody's managed to come up with such a decent trick, to determine some nice looking expression for the operator dual to this overfold ground state. However, when you need to badly enough, using the actual definition of the operator, namely the state dual to this thing, to this ground state, you can work out whatever you want to do that. There was a classic paper by Martinet, Schenker, and friends in the early 80s, I'm sure how to deal with such operators. Okay, but until we need it, which will not be for another year, half a year or so on, we will not be able to how to calculate it. Okay? But just to tell you that there's an issue of, okay, there's only one bad vertex operator. That's one corresponding to the factor. After that, excitations of that are just dead X's. Okay, so yeah. Perhaps the last thing I want, perhaps the last 2-3 things I want to say about this whole this overcoordinate theory is how you combine. Well, the first thing I want to say is how to combine this overfold theory with circular magnification. So suppose you want to compactify on a circle and overfold. That is, you want to gauge the theory, the worldsheet theory, simultaneously by shifts by 2 pi r and by x goes to minus x. Okay? Then how do you work that out? Okay. So first there are the untwisted sectors. The untwisted sectors just take the ordinary theory and impose the gauge projection. That's very easy to do. Right? That's very easy to do because all you do is to you quantize the momentum, you impose that the momentum go to minus itself, and oscillators go to minus themselves under this other shift. So it's just a combination of the two things at the end. Okay? But what about twisted sectors? So the first question is, what are all twisted sectors? Okay? So the first question is, what are all twisted sectors? So x of 2 pi is x of 0 plus some action of the symmetry. Now one thing you can do is to have x go to minus x. Another thing you can do is to have x go to x plus 2 pi r in. But what about combinations of these? You might think that there's a large number of twisted sectors labeled by whether x goes to x plus minus x and how many radii you move by. Okay, so you might think that there are, instead of one winding number, there are 2 winding numbers. That's not right. Let's look at that in one. Okay, you see, let's look at x goes to x plus 2 pi r n, so minus x plus 2 pi r n. This is the kind of thing we were thinking about. Right? So let's draw that geometry. There are 2 cases that we need to consider, n odd and n. So let's take n equals 1 as an example of n odd, and n equals 2 as an example of n. Okay? So, let's say that we've got some value of x. Let's say that we've got some value of x. Okay? And we go from this x to n equals 1. Okay, so what am I drawing? I'm drawing here 0, minus 2 pi r, 2 pi r, and so on. Okay? So, what did I do? I started with, let me start with some value of, with some value of x, let's say here. Then, I go back, I go from there. This is where where sigma equals 0 is on my worksheet. Now sigma equals pi is 2 pi r minus x. Okay, so that's here. Okay, so I've got a string that is centered around pi. Okay? And that's a new thing. That's a new configuration. The kind of configuration kind of boundary condition we haven't seen. But let's look at the same thing with n equals 2. Okay? With n equals 2, I start here. I I want to go to minus x plus 2 pi, and that's here. That's a string centered around 2 pi. But 2 pi is the same point as 0. Okay? So, now of course we go 3 times. We get it centered around 2 pi r plus pi. But 2 pi r plus pi r is the same point as pi r. Okay? So, I'm claiming the following. That if you have a circle compactification, okay, there are infinity plus 2 twisted centers. Okay? The infinity of various winding sectors we dealt with before, which know nothing about x goes to minus x. The plus 2 are simply the kind of orthofold we've studied about x equals 0 and the kind of orthofold we studied about x equals pi. Once we impose the projection, the orthofold projection, namely that shifts are against symmetric problem, all the other seemingly inequivalent orthofolds, boundary conditions of the theory are the same. Is this clear? Okay? So when we study a circle, a target space circle compactified, orthofolded, there are infinity plus 2 twisted sectors. Okay? The infinity of various winding modes we've learned how to deal with allows the circle compactification. The plus 2 are twisted sectors of the kind that we talked about just now. Twisted sector is exactly the kind that we talked about, except that one is centered around 0 and the other is centered around pi. Okay? So, let's make this concrete. Okay? Just to make this very concrete. I'll take 10 more minutes, okay? If you guys have nothing pressing to do, so we've been missing classes and going rather slow. Okay, so let's try to make this concrete. Now to make this concrete, let's try to derive the partition function, the one-loop partition function, the worldsheet partition function of this circle and orthofold compact, right? Circle and orthofold compact. Okay, so let's go. Okay. Because the circle compactification, the orthofold compactification commute with each other, given in either order. Okay, we can think of this as first taking the circle compactified theory and modeling that out by x goes to minus x. Okay, and now what does the partition function look like? So the partition function is a torus partition function. Let's think of this as space in the system. Okay? And there is an interesting way to regard this partition function. You see, what we want to do is, so let's give a name to the symmetry operation that takes x to minus x. Let's call that R. R stands for reflection. Okay, so what we want to do is to take the trace of q to pi naught, q bar to pi naught bar, into 1 plus r by 2. That's project the interstates that are invariant under R. In the untwisted sector, plus trace of q to pi naught, q bar to pi naught bar, in 1 plus r by 2 in the twisted sector. In the 2 twisted sectors. Okay, that would be the one loop partition function, the worldsheet partition function of our worldsheet theory. It's clear, right? We only want to count those states that are gauge invariant. That's what it's projected as for us. We have to sum over the twisted over all the sectors. So that's it. That's all. Okay. Now, what does this R do for us? This R has a very simple action on the fields. On the fields, it takes x to minus x. Okay? So this R operation here, in path integral language, is the same thing as doing the path integral, but not with fields periodic as you go from 0 to tau, but fields periodic up to x goes to minus x as you go from 0 to tau. Is this clear? You know, imagine the derivation of the path integral, and the last step in the time slicing, you've got an operation that changes x to minus x. It's the usual thing, right? So, this can be thought of as half this path integral, which is the one with normal boundary conditions, plus half of this path integral, with a twist with r. By that I mean x on this side, x on this side, not the same, but a minus each. Okay. On the other hand, what about this guy? This guy, we're doing in the twisted sector. In the twisted sector, what does the twisted sector mean? It means that x is minus x as we go down the space circle. So the fact that we're working in the twisted sector means that we've got this R twist here, with a half. That's this term. And, exactly.
I mean, twisted
R. You see, so the full worldsheet partition function, the full worldsheet partition function has this structure. Is this clear? Okay? Now, this is very nice, because you see, this path integral by itself was modular invariant. But it would be impossible for instance, this path integral, this plus this to be modular invariant. Because under tau goes to minus 1 by tau, we flip this cycle and this cycle, and that would take this to this. So this was not there in the theory. If this was not there, okay, the whole thing would not be modular. Okay? Also, this term, under tau goes to tau plus 1, mixes with this term. Because R squares to 1. Okay? So if you've got if on this cycle fields are periodic up to an hour transformation, and in this cycle they're periodic up to an hour transformation, and in this cycle they're just linearly periodic. But tau goes to tau plus 1 takes these, turns the basic cycles of the theory from this to these. Okay? So you can still convince yourself that the only way to get a modular invariant partition function would be to have a sum of all of these things. This thing is modular invariant by itself, but none of these are modular invariant by themselves. Okay? It's the sum of these three that are modular invariant. Okay. Now this is, of course, the structure of why we explained this in the case, in the context of an x goes to minus x over field theory, is very, very generally true for. And you can think of our calculation of the partition function of the circle compactification in this language. If you remember, we gave two calculations of that partition function. First was the Hamiltonian language, then there's the path integral. The path integral language can be thought of in terms. The path integral can be thought of in terms. Okay, but now that we've said all these words, let's actually very quickly write down a formula for this partition function. Okay, so okay, let me write. We could write it down in many situations. But let me write it down in the situation where we didn't have the. Okay, let's do the circle compactification. Which is okay, so we get half of z total. Okay, which is just this term. The circle compactification without any fancy stuff. Okay, but then we get additional stuff. So what's the additional stuff? Well, the additional stuff comes from, let's say, this guy. What's this guy? This guy gives you see, what is this? This is we get a plus half. And then remember that this R here takes k to minus k and w to minus w. Or n, the momentum. The momentum in the x direction to minus itself, and the y in that direction to minus itself. Because it takes both k and k out to minus itself. Okay? Because that's equally an x and x. Okay? So, now, when you can trace, but if kn is non-zero, then it won't contribute to this trace. You see? What we're doing is m sum over m, the states of the theory, times this operator, times r times n. Now, everything here commutes with momentum. Okay? But this flips the value of the momentum. That is to be 0. If k minus k are permanent. Simply w minus w are permanent. Okay? So the first thing that we say is that with this r present here, the only states that contribute are states with k and w equals 0. I mean, momentum and y equals 0. Okay. That's the first effect of this R. Its effect on winding momentum projects you down a zero winding, zero momentum. The second effect of this R is that it acts on oscillators. We see this action on oscillators. It acts with a factor of -1 for each oscillator. Okay? So what does that do? So instead of getting, we get 1 over 1 plus q to the n, product over all n. And then this becomes plus. No, instead of the underset. Okay? Because each insertion of this Q is an insertion of an extra oscillator. Okay? And with this you should regard as 1 minus of minus Q. So every time you have an extra oscillator, you can get an extra minus sign along with the energy wave. Right, because R just weights the trace by -1 to the power number of oscillators, which is what this thing is doing. Okay, and then the final thing that we have, of course, is 0-point energy. We're still in the untwisted sector, so we get plus q bar to the power, what is it, minus, okay, right? Okay, so we dealt with this guy and this guy. Now let's deal with this guy instead. What's the effect? Well, let's first do this. This guy is simple. Here what we get is simply product over all n, 1 over 1 minus q to the power n plus half. 1 minus q bar to the power n plus half. And we have to deal with a strict 0 point energy, so this becomes q bar to the power plus 1 by 4. There's no half here. Each of these two terms came with a half. There's no half here. Why? Okay. Readable fashion. Yes, why is there no half here? Somebody?
There are two places.
Very good. Because there are two twisted sectors. That compensates for the half. And finally, there's this term. Okay? That term, all is the same thing here, but with the minus signs of these oscillators. So we get q bar to the power 1 by 48, part of n, 1 over 1 plus u to the power n plus power 1 over plus to the power. And that's the answer. Notice we didn't even have to talk about winding and momentum modes here, because there's just, in the twisted sectors, there's no contribution from Z, there's no zero mode. Alright, so that's the full answer for the partition function of the Ormsby problem. Did you get it? And it's far from obvious that the sum of this plus this plus this is modular. This is obviously modular merit. Far from obvious that the sum of these three is modular merit. However, mathematicians love these things called theta functions. All of these things can be written as the theta functions. And turns out that the modular invariance of this is a classic identity of theta function. We may need to discuss this at some point, and if so we will. But until then, I'll just ask you to take it on faith and we can directly verify the modular invariance of the sum of these three functions. Okay? Okay, now absolutely one last thing before I let you go. First questions or comments? Questions, comments? Okay. So, now, absolutely one last thing. Okay. And this is about the space, the space of C equals 1 conformity. Okay, so far we have, what we've been doing in the last 2 or 3 lectures is studying worldsheet conformity field theories with central charge equals 1. All this circle compactification, the awkward compactification, because none of it has changed the value of the central charge. That's determined by local OPEs, which remain unchanged. Okay, and now I'm going to describe for you the set of all known C equals 1 conformity. Yes? I don't think there's proof that this is all that it is, but it's believed that it is. Okay? And we find a surprising equivalence. Okay, so first let me tell you about that equivalence. And then I'll tell you what the space is. Okay. So let's see. Suppose we're at, this overfall theory can be studied at any rings. Okay. So, suppose we're at the self-dual radius. Okay? R is equal to square root alpha, right? Okay? And I do the x goes to minus x over. good point. You might think it's plausible, and it's certainly true, so this symmetry is part of the SU2 times SU3. Okay? So let's try to study it. Let's try to see what part of the SU2 times SU3. You see, let's look. Let's look at what happens to the currents of the SU2 times SU2 as x goes to minus x. See, Jx was equal to e to the power I2 by square root alpha prime x plus e to the power minus I2 by square root alpha prime x. Xn doesn't matter for this purpose. By 2. Jy was equal to e to the power I2 x by square root alpha prime plus e to the power minus I2 by square root alpha prime x. So minus by 2i. And Jz was equal to I by square root alpha prime then x. Now let's take x to minus x. See what happens. What happens is that Jz goes to minus Jz. And Jy goes to minus Jy. Okay? But Jx remains